Okay, so we're going to watch a video to get back into the swing of things, right? So I love videos too, that's why I showed them this video. So this is the video. If you're watching digitally, watch this video or the one I put in the link down there. I'm going to turn off my sound for a second and stop the recording so we can watch it here. So watch this video if you're watching digitally, and Dr. Kep's going to show the video in the remote location. Okay, so hopefully everyone was able to watch that video. I thought it was appropriate considering our next activity. So like I said, you're going to do this individually. Don't put your name or any identifying marks on it, because other people in the room are going to look at it for algebraic thinking, right? So I'm going to give you an activity, complete it by yourself, and think about the algebraic thinking when you're solving it. I know you're not going to have a lot of time, so you might not be able to finish it completely, but just when you're writing solutions, think about how you're thinking about the problem algebraically, right? So with the, let's see, the activity is the following one. I'm going to pass out. So I have it on there for the digital people who want to start looking at it. So like that individually. Show us some examples of how you can write numbers as the sums of consecutive numbers. So the examples up there are 15 is 7 plus 8, and 7, and then 8 is consecutive. 9 is 2 plus 3 plus 4. And that's why I keep backing up the problem. My apologies. You guys doing it. So, basically the activity is to figure out how you can write certain numbers as sums of consecutive numbers, right? So you know this thing, you have to example 22 is 4 plus 5 plus 6 plus 7. So you can write 22 as a sum of 4 consecutive integers, so counting numbers, what they call them. And you could take, maybe you could write 22 as the sum of a different number of consecutive integers. In fact, there's extras of everything I handed out if you want to grab some at the end too. Okay, so you have 30 minutes to complete this activity. So I'm going to start a timer for 30 minutes. I'm sorry, yeah, we're done. Oh, whoops. Timer starts now. Sorry, I didn't mean to skip you. They say counting numbers, so. Yes, I would say counting numbers would start at 1 probably. When you say natural numbers, some people would say that starts at 0, and some people would say 1. So it's a matter of preference. If you want to include 0 as a counting number, you're welcome to, but it's not really a counting number. You can't count up by 0. So. Okay, so you have 29 more minutes. And I'm going to share with the digital people who are watching at home, share the entire activity. So the activity is, for each of the numbers 1 through 35, find all the ways to write it as the sum of 2 or more consecutive counting numbers. So counting numbers starts at 1 and goes up as high as you want. So make a table like this. Maybe. I'll let you answer that question. Just be prepared to justify your answer, that's all. Notice there are several questions that go with this. In fact, I have another sheet which has some other questions on it. I'm going to pass this off. Okay, so now we're going to discuss our answers. First thing I'm having everyone here do is staple their papers together so we can pass them around the room. And once you staple your papers, just leave them on this table because I'm going to mix them together and pass them out for both. It's okay if you didn't get to everything. It's not. I know it's kind of a long problem for 30 minutes to do by yourself. Some people we're working together and it still is kind of a long problem. But, so, we're going to look at a couple of specific rows. I think the best you put in that file is don't discuss it. That's fine. Is there anything to do like the table or? Because we're going to have to I guess that's fine because we don't have to have. I'll probably pass it out in groups so you can look at your table. So each table will have, like 3 papers. That's fine. So we're going to look at a couple of the rows. I'm not going to look at the whole table, just a couple rows. Okay. So let's look at, so someone pick a number from 1 to 9. Or 2 to 9. 7. Okay. Could you write 7? Does 7 have any way you could write it as sum of 2, 3, 4, 5, 6, yes. Or 7? Yeah. Which way? 2, how? Any other way? 7 fit into any other of the rows? No. Someone pick a number from 10 to 19.
17.
17. Does 17 fit anywhere? There. Should it fit anywhere else? What about, I don't think they get letters, but you put in 21. So the 10 plus 11. What, anywhere else?
7, 8.
You said 3 numbers?
Yes.
6 plus 7 plus 8. Anywhere else? Anyone get the 6 numbers? Yeah. So you notice that some numbers can be written as the sum of different numbers of consecutive numbers. So 21 can be written as the sum of 2 consecutive numbers, 3 consecutive numbers, and 6 consecutive numbers, right? That was the first one that fit into the 7 column. 28, so that's 1 plus 2 all the way up to 7, right? Which in the table had the most entries in a row? 2? So 21 had 3 entries, right? Was there any with more than 3 entries?
I didn't notice that.
I shouldn't have even noticed. That's all right. I don't know the answer. I didn't look at it myself, but I can look at someone here. Like page 15, they filled out has 3 entries, and 1 has 3 entries. Looks like 30 was somewhat interesting and has 3 entries, but different than those. So how can you write 30 in it? 30 was apparently 9 plus 10 plus 11, and 6 plus 7 plus 8 plus 9, and 4 plus 5 plus 6 plus 7 plus 8. Right. So a little different than 21. 21 was 2 numbers, 3 numbers, and 6 numbers. 30 is 3 numbers, 4 numbers, and 5 numbers. Okay. So, filling out. What's one of the purposes of filling out this table?
So you can look for the patterns and come up with the rules.
You can look for patterns. You can't look for patterns if you don't have some information, right? So, filling out the table was collecting data to get some information to answer the other questions which we're asking about patterns. So, the second question, which I'm going to do this for the digital people. So if you're watching this by yourself, try and answer these questions as you go along. You can even pause for a minute if you need to. What patterns do you see in the chart? You might look for numbers that can be made by a particular length or of sum, or how many different like sums can make particular numbers, or which numbers can't be made by consecutive sums. Use your imagination. So patterns, period. Right?
Okay, so 3 consecutive numbers counted by 3 in the column, 4 consecutive counted by 4, 5 consecutive, and so on.
Four.
5, 6, and 7. Over the same.
All right, so that's one pattern. So to go from one that can be written as 3 consecutive numbers, we can move 3 down to get to the next one, 3 down. Any other patterns? 2 was all the odds. 2 consecutive.
With the exception of 2.
Number was all odd.
The exception was 2.
Huh?
1 plus 1 is 2. It's not?
1 plus
I'm just kidding.
So you can only make odd numbers at the sum of 2 consecutive numbers. So that's one pattern. Any other patterns?
Can we Google it?
We have collected a Google of information in our brain.
Well, the average of the numbers for the odds is always going to be the middle number, and for the evens it's going to be a half number, and then the multiple is always, each consecutive sum is always a whole number more than the previous average.
So the average of the odds is the middle number.
And it's always the middle because it's
So you're saying you get like 1 plus 2 plus 3 plus 4 plus 5 divided by 5, you get the 3. That's kind of what you're saying? You get the middle number?
right, it's 15. So it's 3 times 5, the average. But if you go to the next number, it is 4 times 5 is 20.
Right, so 2 plus 3 plus 4 plus 5 plus 6 divided by 5 is 4. And you said, what about the evens?
It's the same for the evens, except the middle number is going to be a 0.5.
Oh, so it's halfway so the average is halfway between the two middle numbers, you're saying? Yeah, it would be like 1 plus 2 plus 3 plus 4 divided by 4 is 2.5, right? Which is the average of the two middle numbers, okay?
So then the next number would be 3.5, and if you multiply that by 4, that gets you the next sum sequence.
Right, so 2 plus 3 plus 4 plus 5 divided by 4 is 3.5. So you can get to the ones that can be made. So you're saying you take 2.5 times 4, 3.5 times 4, and so on to get the numbers that can be made, right? So this top is 8, 14, which is 3.5 times 4, right? Because 3.5 times 2 is 7, times 2 is 6. So yeah, you can think about a pattern of how you can make consecutive numbers. So one thing you can depend on is whether there's an even string of numbers or an odd string of numbers. So if you're adding 5, there's odd amount of numbers, 6 is an even amount of numbers, and so on. Any other patterns? All right, so if we move on to the next question, number 3. What predictions about sums of consecutive numbers can you make from these patterns? Write a rule if you can. And how general is your rule? Yeah, but they said they were going to work on their own. So, any rules that anyone came up with? That's kind of a rule if we generalize it, what we just stated.
For chocolate numbers, though. I did one for all of them. Like I did one for 2, 3, 4, 5, and just did n plus 1 for 2. And then you get qn plus 1, and that was my general rule for 2 consecutive.
And you notice that's the definition of an odd number. You can do it like that.
And then I did it for 3, 4, 5. I did it on my paper, but I did it
so like you did just kept one like this?
Yes.
Which is 3n plus 3. So on.
And then I factored it out.
So you could rewrite this as 3 times n plus 1. And you did down to 7, or you did?
I did down to 7. I didn't do for just in there.
You didn't do it for 7.
I did 14 down to 7.
You did it for up to 14 consecutive numbers? What's the 14?
14n plus 91.
14n plus
91.
Is what? n plus 1
I didn't write on yes.
plus n plus 13, or is that, or does it start somewhere else? I guess you can figure out 1 to 13, and 13 times 14 divided by 2.
And then that's
right, that's what it is. Any other, did anyone do it completely in general?
Because I didn't do the n plus 1% all the way to 13. I just did the pattern instead.
So like you're saying, this kind of number can be written as a sum of 7 or 14 consecutive numbers.
Right, but I didn't add the n's and add all the 1 to 13. Like I didn't do it that way.
Sorry, I generalized. I made
right, no, I know, but like I'm just saying, like so the thinking behind it, like for an even number, you kind of still I was still looking for a way to write it as far as an algebraic kind of way, but like for even numbers, you take the number of sums, and then you
consecutive number. So you're going to rewrite the number 2n, that's an even number, as the sum of n consecutive numbers.
and then you multiply it. So, for instance, like for 10n, it's like 10n plus 45, because you do like 10 times 5 minus 5. So you're basically doing 9 times. You do one below that.
One below what? The
The
2n?
number of sums you're looking at, and
So
then yeah, we're still looking for the pattern. Like I can apply the pattern going in order, but like for 2, it would just be like 1 below that, so it's just a 1. But then when you go to 4, which is the next one, you would end up doing 1 below 4, and then 3 times 2, so it's going to be 4n plus 6. And then for 6, you go 1 below that, so it's going to be 5 times 3, so it'll be 6n plus 15. You see what I'm saying? It might make more sense on my paper.
Yeah, it's hard to visualize what you're saying that fast in my head.
So you take 1 less than your n coefficient,
So 1 less than your n, so n minus 1.
and then you multiply times what even number that is. Like if it's the first even counting number, the second even counting number, the third even counting number, that's what you multiply.
Oh, so n. That's what n would be.
Yeah.
Because if n was 1, 2 is the first even number. If n
Yes.
was 2, 4 is the second
Yes.
even.
So you take, 1 less than your sum number of sums times the number that the even number that is. And then for odd numbers, it's
And 6, that's it?
That's for, well, you have your, okay, hold on. You have your 2n out front.
2n?
That'll be 2n plus that expression.
That or
For
2m. M is the number,
of sums?
no, n is the number of sums. M is the
The number of even
number of, the rank it is of even numbers.
So then I would have, that would work. And then for 4, it'd be 4n plus 6. So let me see if that would work. No, because now we're looking at rank. So that should be 2n.
M?
Yeah.
So your even number
Rank.
plus the rank of your even number times 1 less than the number of sums. And this gives you what?
That's your general pattern. Like it should give you 2n plus 1, 4n plus 6, 6n plus 15, 8n plus 28, 10n plus 45, 12n plus 56, and 14n.
Because I'd like to say, can I write 2m as the sum of n consecutive numbers?
That's what I was trying to get to the next.
But this is, what does this tell me?
A generalized expression for how to get like an even sum. So like 14 would be 7. Right? So then let's see if that would work.
So you're saying if you plug in a number for m, and you just plug in this expression n, then you can write that number that you get
That expression.
as the sum of, and this is not guaranteed to be even, though.
Well, I have a different expression for even numbers and odd numbers.
That's what I'm saying, that this number can be both.
Yeah, so you have to be having that.
This can be odd, so this could be either, this could be even or odd. I'm probably not writing it how you.
Yeah, it's like, I could maybe have to do it.
What if we did this kind of way, kind of organized it a little bit, I think. Because if you took n plus 1 plus all the way up to n plus m minus 1, how many consecutive numbers is this? This is m consecutive numbers, right? And it's not that hard to add this up because this is n times m. Because you have an n here and n here. Each one has an n in it, so you have m n. And then you're taking, so this one doesn't have a number after that. So you have 1 all the way to n minus 1. You have the Gauss's sum formula. which says that this is m minus 1 times m over 2. Right? So that would be it. If you want to find out if a number can be written as a sum of n consecutive numbers, any number like this can be written as a sum of m consecutive numbers. Which I think is what you were, it might have been what you had. So this would be completely in general. Can you write the number as the sum of n consecutive numbers? Well, if you plug the n in here, and you can find an n so that this expression is equal to your number, then the answer is yes. If you can't, then it's no. Well, you can look at an example. So let's look at an example. So someone pick a small two-digit number. Relatively small. 13 was say first and 18 was say 13. So the question is, when you did 13, could you write it as anything? What? 6 plus 7, so it's 2, right? So if you were trying to see, can I write 13 as some two consecutive numbers, my n would be 2, because that's the number of consecutive numbers. And so I plug that into this expression, I get n times 2 plus m minus 1 is 1 times 2, so this is 1. So can I find the number n, so 13 is 2 times n plus 1? Well, the answer is yes. N would be 6, right? Well, what does that tell me? That tells me that 13 is 6 plus 1 bigger, 7, right? So this gives you the starting number to start adding. Two consecutive numbers starting at 6, 6 plus 6. Okay. What about 18? Did you write 18 as the bigger? 3 consecutive numbers? Okay, well, you could do 4 as well. Let's do 4. So let's say m is 4 here, right? If we plug it into this formula, we get n times 4 plus 4 minus 1 is 3 times 4 is 12 divided by 2 is 6, right? So can I write 18 as 4n plus 6? Well, if you had to do it, then this had to be 12, so n is 3 here, right? 3 times 4 is 12 plus 6 is 18. So what does that tell you? 18 can be written as some 4 consecutive numbers starting at 3. This is the starting number. What? And I think that's what you're driving at, so that's... Sorry, I kind of... Okay, what about the fourth question?
How did you go from the n times 4 plus 6 to 3? Oh, thank you.
Is that here? Yeah,
Yeah, she answered it.
I made these before.
You're good.
Sorry, I kind of did that really fast.
I process slow. I have an IEP. Do you even know what that is?
I've heard this, but I forgot what the acronym is.
It's an individual education plan for special ed students. And it would not be a disability.
Okay, so number 4 says if you haven't already, look at just the numbers that can be made by a sum of 3 consecutive numbers. What patterns do you see in those numbers? How can you predict whether a number can be made as a sum of 3 consecutive numbers? I guess we kind of just did a lot.
Gauss.
Gauss.
G-A-U-S-S.
Well, Gauss came up with Gaussian normalization. He did a perfectly large number. Number 3. Number 3. Well, I think the old tale is that Gauss, I'm pretty sure it's Gauss, was in elementary school. The teacher wanted to occupy the students for a long time, said out of the first 100 numbers, and he did it in 10 seconds. because we knew it was 100 times 101 divided by 2. You saw the pattern. The reason is because you add up the first 100 digits, you can group the first and last, the second and the second to last, and so on, and they're all the same. So that's the tale. Who knows if it's true or not?
It is true. I would say.
Yeah, okay. So we have one eyewitness. You need 2 eyewitnesses for verification. Okay, so we kind of already looked at this, but what pattern do we see for 3 consecutive numbers? Not looking at the general pattern I wrote down already. They're all multiples of 3, exactly. And starting with 15. Starting with 6. They're all multiples of 3. And the way that we said earlier was written as 3 and 10 plus 1, I guess. Right? We said 3 times n plus 1 is n plus 1 plus n plus 2, right? Why is that? Because you can borrow one of the ones here and move it over here, and you have 3 n plus 1, right? You want to look at it like that. So 3 times n plus 1, if you can write it that way, you can write it as a sum of consecutive numbers. What's the first n you can put here? 1. That's why 3 times 1 plus 1, which is 6, is the first one. Because n has to be at least 1 for this pattern to work. Because we started with counting numbers starting at 1. If we would have gone down to numbers below 1, we could have maybe done something different. Okay, so for 3 consecutive numbers, it's a multiple of 3, it's starting at 6. Then you can. What about question 5? Do the same thing for 5 consecutive numbers. So they're all multiples of 5. So it goes up by multiples of 5. What is it?
You can start with 10.
So you could say 5n plus 10. And n has to be at least 1. Right? So if you write it as 5, you write a number as 5n plus 1 starting at n equals 1, you will get all the ones that can be written as consecutive, 5 consecutive numbers. Why does this work well? Well, because 1 plus 2 plus 3 plus 4 is 10, right? So you have 5n plus 10 more, right? And you could think about it again. You could borrow one of these. This is 5n plus 2. Right? So you could borrow one from the 3 and put it to here to make that n plus 2. 2 from here and put it here, so you have 5n plus 2. You were kind of hinting at that, thinking about the middle number as one of the keys to this, right? So the middle number here is n plus 2. So for 5, it has to be multiple of 5 here. Right? And both of those were what kind of numbers? Can 3 consecutive and 5 consecutive? 3 and 5 are odd, exactly. So that's why the middle number, the average of the middle numbers, or the average of the numbers was an actual whole number, right? N plus 2. What about 6? Make a prediction about the sum of other odd numbers of consecutive numbers, like 7, 9, or 11. So what about, we did a general pattern, but we didn't look at it in terms of even or odd. So what about 21 consecutive numbers? What kind of number is that going to be? What do you think? So remember, for 3 we had 3n plus 1. For 5 we had 5n plus 2. So what do you think for 7 you're going to have? 7n plus 3 maybe, right? And for 9 you're going to have 9n plus 4. So for 21 you're going to have 10. So if you can write a number as a sum of 21 consecutive numbers, it has to be a multiple of 21, and it has to start at 21 times 11, right? That's the first one that can be written. But then has to be 1, 2, 3, 4. So 21 times 11, what's that? 231. It isn't that. I think it's correct. So 231 is the smallest number that can be written as the sum of 21 consecutive numbers. And it would be 1 plus 2 all the way up to 21. Right? And you think, once again, the middle number. So this is 1 plus 2 all the way up to 21. The middle number in that list is what? What's the middle number of the first 21 numbers? What's that? Well, the middle number is what's here. So we're seeing patterns. Does this rule work for the sum of even numbers? Can you do the same rule for even numbers? So if I wanted to write 4 consecutive numbers, should I say that it has to look like 4 times n plus something? .5. So you could maybe think about using this pattern, right? Because 4 consecutive numbers, so it can be written as sum of 4 consecutive numbers. It has to look like 4 times n plus 1.5, maybe. Does that work? So if n is 6, that doesn't work, isn't it? So if you multiply this out, you get what? 4n plus 6.
That's right.
So does it work?
But if we're at 6 and 6 times n plus.
Oh, but for 6 it would have to be in here, right?
Oh, yeah.
So it would be 6 times n plus 2.5. So you could actually use the same pattern.
Yeah.
And why is that always an integer? Why is this an integer? Because you have a non-integer here. Because you're always multiplying by 2 at least, right? Because you have so you could actually write this pattern, and this is always going to be. So if you had a general even number 2m, what does this pattern tell you that? 2m consecutive numbers, not 2m consecutive numbers. What does that kind of number have to look like? Two m times
2m minus 1 divided by 6.
So it's n plus what?
2m minus 1 divided by 6.
2n minus 1 divided by 2. Yeah, I think that would work, right? Because if you look at our pattern, so we always take 1 less this number, 6 minus 25 divided by 2 is 2.5. 8 minus 1 is 7 divided by 2 is 3.5. So if we take our number, 2n, I don't know if you can see that. And we know 2n minus 1 divided by 2 is always going to be a non-integer, right? So you're taking an odd number, or you're taking an odd number divided by 2. Always. So you could actually make this pattern in general if you wanted, right? You could say, if you wanted that, well, I guess it would be hard because we set it up. No, I guess if we had k consecutive, well, I guess we were doing m consecutive numbers, right? So if I had m consecutive numbers, what is this pattern telling me it has to look like? So that would replace the 2m, right? So this is m, right? So we had 2m consecutive and m consecutive numbers. If I fit it into this pattern, it would look like what? M, my number, times n plus okay, right? And if you look at that, if you distribute this, that's exactly what I wrote down. Right? So this pattern does work even for even numbers, as long as you're okay with having a non-integer in the pattern, right? Or in the formula. If this number is only an integer if m is odd, it's not an integer if m is even. Okay. And the last question, use your rule to predict whether each of the following numbers can be made with 2, 3, 4 consecutive numbers, etc. So let's look at, let me check back in with the, we're back with you now. Okay, so they're back. So Warren, we're looking at the last question, which was predicting whether the numbers can be written as the sum of 2, 3, 4 consecutive numbers, etc. So let's look at 57. How about? So 57. 2. So this is the number of consecutive numbers. So can you write 57 as the sum of 2 consecutive numbers, 3 consecutive numbers, 4 consecutive numbers, 5, 6, 7, etc. So predict. Can you write 57 as the sum of 2 consecutive numbers? Yes. Why? Because it's odd. Every odd number can be written as the sum of 2 consecutive numbers. And you can check what they are. In this case, it would be half of it minus 1, right? Or sorry, take the number minus 1 divided by 2. 56 divided by 2 is 28. Is that right? So let's ask Martha, could you write 57 as a sum of any other number of consecutive numbers? I'm going to ask the online group that. So Dr. Kep, could your group write 57 as the sum of any other number of consecutive numbers rather than 2?
We are looking into that right now. I think I inadvertently did not hand out all the pieces of paper I needed to at the beginning, so that being the last question, we had not had a lot of time put into that. That was my bad. Oh, they're telling me
that's all right, because our group didn't want to get to it either. So.
Okay, great.
Even when they had it. So.
Well, okay, so they just tell me that 3 works. You can write it as a sum of 3 consecutive integers, or counting numbers.
somebody can put 3. 57 minus 3. 64 divided by 3.
Good. So yeah, that's right.
And remember, the middle number is the number. The middle number is get rid of 18 plus 19. That was the first factor, one other factor that was suggested. Can you write any other number of consecutive numbers?
So, how do you do it, right? Divided.
So 4n plus 2.
Divided by what? 2? Or do you have a 3? No, it's of course somewhere. So, 0. 6 will divide 1. Yeah, 2 to 4, 16. No, 16. 17, 18.
So
it's 18 message. Yeah. Divided by 7.
let me see.
What else? Yeah. Right. 7. 6. And then 4. That was what? 57. Yeah. The same 57 was 3 was 6.
And you write 57 as 6 plus 5, which is 10 plus 7 minus. Right at 7 plus 3. 56 minus 21 is 35.
Throw in one more idea. I don't know whether to share this with the whole group or not.
How far do you have to go? So if you square the number of consecutive numbers that you get to straight here, I think 7 squared is 49, 9 squared is 64. So you can write think about 1 plus 2 plus 8. There's already 8 times 9 divided by 2. Now I guess you'd have to square and divide by 2. Think about you can stop because 1 plus 2 all the way up to 10 you stop once you get that spot because the smallest number can start at 1, right? So you think from 8, 8 times 9 divided by 2, 4 times 9, that's what it's going to do. 7, 8, 9, 10, 1, 12, 3.5, which is 8 and
Okay, so what he's given there is the formula for the fraction.
well, 8 and what kind of number on that?
You might have encountered that somewhere in in the context of a textbook, they often will give a story apparently Euler and the teacher gave them the problem of adding up the first 100 numbers, 100 counting numbers in order to
is 21, and 21
busy. Euler solved it instantly. And the way he did it was to say, well, we could take the n and the 1 and add them, and the 2 and the n minus 1. And what you get is n times n plus 1, and how many copies of it do you get? Well, you get the total number divided by 2. And so you get that formula. Once you have that, well, that tells you the first number that's going to be in the So the first number in column n, the first number that can be written as a sum of n counting numbers is going to be n times n plus 1 over 2. And if you check that,
No, right, because
where you started.
57 minus 45 is 12, and that's not a multiple.
And so when you're trying to figure out which numbers can work, that was the approach that initially came up over here.
So think about in your table one more of those.
Right here is that the number here, when we started at 0, you had to look like to be in the fourth column.
So let's look at that's a good question. So let's think about that for a second.
Which is 4 times 5 over 2.
So the suggestion was
10. And so if you're looking at a number and you want to know that it works, you just look at the triangular numbers. And if your number can be written as k times x plus the kth triangular number, so if I can write this, if n can be written as k times x plus the kth triangular number, that says that n minus the kth triangular number is a multiple of k. And so if you take each of the triangular numbers and subtract them from your candidate number, then if you're subtracting the 10th triangular number, if you don't get a multiple of 10, then you can't write that number as 10 summing. So for instance, if you're looking at, say, 75, and you want to know, can it be written as 6 summands? Well, you take the 6th triangular number, which is 6 times 7 over 2, 21. You take 75 minus 21 minus 2 is 5, 54, and that is a multiple of 6, right?
So why not multiple of 2?
9. And so yes, it can be written as a sum of 6 numbers because of that form and the fact that everything's in whole numbers, so the visibility actually is important here.
So that, I mean, 2
so
itself is limited.
This makes it a little bit more clear and concise if we are looking at, you know, the idea of starting with x greater than or equal to 0. That tells me that when x is 0, the first entry in my column is the triangular number corresponding to that number of summands. And then the fact that we ended up going up on multiples of the number of summands is manifested by you take your candidate number, subtract the appropriate triangular number, and ask, did I get a multiple of the number of summands? If I do, then I can do it. And this is 6 times 9. And so in fact, that tells me it's going to be 6 times 9 plus 21. That's going to be in row 10. Or it's going to be the 10th number in that row. That column, I think.
So it is a multiple.
We start at the first one and we add,
You're using an odd number.
from the first one we add 9 copies of
So you definitely can't write a power of 2.
And none of this, you know, I feel like we're getting a little far afield because the point is really to focus on the thinking, not so much
You can't write a number 2 numbers, so that's what we call. So if n is any number bigger than 2, I guess 4. So you say like that's even. Okay, but for odd numbers, n is odd, definitely can't write it. Odd number, as an integer, is definitely not multiple. Remember, n is odd. What's wrong with it? Why can't you find a multiple of 2 looks like this?
So let's see. Oh, he's looking at the question of whether powers of 2. Somebody must have come up with that.
You can always have Well, if it's this odd, it's even, so that is even. You think, so now that it's 2K, you're going to have 2K, plus NK minus 1 over and it's supposed to have 2K. So this number is going to be a half number, not a half number. In between integers, right? Not really in fraction. So why can't this number, well, because this is an integer, this whole thing, right? Why can't it be okay? Like you think, you bring in 2 in, you get what? You get K times plus 2K minus 1. 2.
Oh, it's like he's looking at the powers of 2.
What kind of number is this?
What causes them to stand out in your chart? So look at all the rows that are powers of 2.
K times 2 plus K minus 8. And number is this. No, it's odd. This is an odd number.
1 and 2 and 4 and 8. 16.
Now, if you want to be a multiple of 2,
What's coming up, you said?
it would have to be a multiple of 2. Otherwise, it's not going to work.
We're looking at the question of these numbers cannot be generated in some consecutive intervals. And if you look at it, are there any rows in your chart that are empty that are not powers of 2? Right.
I thought it was a good question. I thought it was a really good question. And I think they kind of asked that right in this power. That was a good question.
So then when you look at that pattern, you have a conjecture that maybe.
So let's finish by doing one last number.
What I was trying to get at is some
let's do 80. So part E.
But
so at your table, including Martha, can you write 80? 80. Number of can you write 80? 2, 3, 4, 5.
okay, we have a method.
So I'll give you 5 minutes to think about this one question. And if you're watching this at home,
Okay, so we got 5 minutes to figure out so we can write 80. And
your solution to 62 and 75. How many ways can you write 62 as some of consecutive numbers and 75 on your Facebook post when you post everything? If you're watching this digitally at home, on your post that you're going to put on Facebook, put how many ways you can write 62 and 75 as some consecutive numbers.
Wow, 74 divided by 3. 74 divided by 3.
And once we finish this, we'll take another 5-minute break.
So you have to write this. These 2. Yeah, and all of these. 2, 3, 4, 5. 5 all the way to minus 15. Another vertical is 13. 2, so describe. So 18 plus 15 plus 16 plus 17 plus 11 plus 16. Yeah. What did you get? Yes, number 5. I mean 5. So far. 80 minus 21 divided by 6. 1, not 6. 7. Divided by 7. So A should be what? Not 7. Plus 8. 36 plus 8. 80 minus 46. 3, right? 4. 8 is no. 9 should be 45 plus 9x. And 10 should be 31. So 55 plus 10 is 16. 17. 80 minus 45. And 19. Divided by 9. 80 minus 55 is first number with you get it with 3, you get 3, yeah, it'll be 14, 15, 16. When you did the math, when you divided by 5, you got 13. So go to the next one, that's where you start. 14, 15, 17. So, just 8. Huh? 15, about 16, 17. That's 33. So, 89.
Okay.
11, 12, 13, 14.
No.
Huh? 11, 12, 13, 14. I know.
5.
So what's the consensus?
5. Did you 11, 12, 13, 14? Okay. So,
It's
I don't think it's
yeah.
And go into something 45.
correct.
The next week.
All right.
That's what it's supposed to be. You have the 13th one?
Yeah, I see it. 14,
All the way to 13th.
14, 15, 16, 17.
14, 15,
14 to 18, yes.
Huh. It's not apparently sending my
Little message.
my chat permission is off, but I'm a moderator. How do I turn my chat permission back on?
Actually, it just it didn't take away numbers.
Okay, so let's say I'll go down the list. They have a complete answer. So let's let Marfa give us their answer, and then if anyone disagrees, you can let me know. So what is the I don't know if you're talking. Let me turn off my microphone.
Except you didn't hear that. We believe that only 5 words, right? Everybody 5?
Yeah.
All others are impossible, and the only ones you have to check are up to 12 inclusive. And that should be all.
All right. So you said, Anyone disagree? Why do you only have to check up to 12? What's 13 squared? Divided by 2. 84.5. Bigger than our number. That's an approximation. If you want to do the actual one, it would be 14 times, or 13 times 14 divided by 2. This is the basic problem. Okay, so only 5 works, and how can you write 5 as the sum of consecutive numbers? Sorry, what? 14. All right, so let's take a 5-minute break, and we'll come back and we'll do your mathematical thinking, record reflections, and then we'll look at some other students' work on this same problem. So, and then we'll look at your work too. So we'll take a 5-minute break, come back at 2:50. Okay, so now we're going to look at, I'm going to pass out more student example work. Oops. Now, where is it is the question. Oh, it's in the next session, this one. Okay, so we're going to look at example papers for sums of consecutive numbers, this problem. So discussion guidelines are compare the way students E and F, so there's two different students here, students E and F. There's actually students E, F, and G. So compare the way the students E and F go about building rules, what patterns, so on. And the other two students, student G, notice the patterns come up with the rule, however the student shows evidence. Did I not print out I'm not going to print out that part. I just printed out the student work. So I'm going to leave these questions up here. So first of all, look at this first question. Consider this first question. Okay. So actually, it's probably easier for one to graphics. First one is the same thing as student analysis, so you have a little table where you can fill out information. Second one is student F work. And then, sorry, student G work should be first. So we have student G work, student F work, student G work right here. Okay. Yeah. So here's a couple of the discussion questions up here. They're similar things to what we did on the other group of work. Let me, for those people that are digital, we have a similar table, student work analysis sheet. Then we have the student work. So I'm going to go through the student work. At this level, student E has 4 pages of work. Let me write it at 6. Here's page 1, page 2, page 3, page 4. No, that's why I'm leaving them up there.
Oh, okay.
I forgot to print out the discussion book. Student F, page 1, page 2, student G, page 1, page 2, page 3. So you're looking at filling out the student work analysis sheet, thinking about these questions. So the questions are, Here's the other two questions that you should be thinking about. So I'm going to give you 20 more minutes to look at them. So I'm going to set a timer for 20 minutes.
But
All right, so the time's up. We're going to move on to now a group discussion about the algebraic, the direction of the students' thinking in the example paper. So what direction they were thinking. So as a group, including Martha, if you want to interject anytime, we're going to look at these 4 discussion questions. How could students E and F pursue their lines of thought to come up with more general rules? How do the patterns described on students' G's work relate to underlying mathematics in this problem? How might students' G work towards justifying generalization? What other ways do you see these papers show the potential for students to expand their algebraic thinking? In what ways do you see these papers show the potential for algebraic thinking learning difficulties? For example, you might look at one of our papers and say, if they only pay attention to blank instead of blank, they go farther. Right? So let's think about the first question. How can students E and F pursue their lines of thought to come up with more general rules? Any suggestions? Okay. So they kept it more informal, I guess? Any other suggestions on how E and F could pursue their lines of thought to come up with more general rules?
Well, he was starting to be there for the following.
Well, he was starting to be there. What did they get?
Negative integer formula. And they will start to apply.
What did they put in the bottom right of the first page? But did it have to be prime? No.
But I like the way that they did the remainder so that if that number that is so they said it that.
Yeah. Well, they understood remainder. That's a pretty important idea. Is there any other way that students E and F to pursue their thoughts to come up with more general rules? And if you're listening to this at home, think about these questions as well and write up at least a couple sentences about 1 or 2 of these questions. Or if we move on to the next question, or Warren, if Martha has anything to ever interject, just let me know so I can turn off my microphone so we can hear what you're saying. How do the patterns described on student G's work relate to the underlying mathematics in this problem? And how might student G work for justifying these generalizations? So if you look on the second page of student G, he wrote some rules down, right? Or he or she, sorry. Maybe student E cheated off of student G. Yeah, and that's something that we discussed at the end, right? So they came up with this idea. They realized that if you have 2 to a power, it's impossible. We write it as sum of consecutive numbers. They didn't justify it, but they realized that from the patterns, right?
No, and they didn't put 2 to the second power, but, that's not how that actually.
Right, they said 2 to some power, right? They gave us some rules. The higher consecutive numbers are listed, the more the space they leave in between. They didn't say what space they leave in between, right? Which we discussed that. If you have 10 consecutive numbers, they leave, I guess, 9 spaces in between because it takes the next 10 lists to go down. Odd numbers have a better chance to have consecutive numbers than even numbers do. I can't really justify that, but what about question 3? What other ways do you see these papers show potential for students to expand their algebraic thinking?
They have to put it all together for the big picture. They can't seem to just, come up with one general rule for everything. I mean, they get the right rules for each, for the different numbers, but as far as thinking globally, they have a hard time. And that may be because we for so long, made them be real, specific about the stuff we haven't, asked for, general stuff.
It's easy so much at high school level. When I was going through school, we didn't do much work like this. I went to school, I teach it now. You're just trying to hope they walk out with some understanding of fundamentals of math. So, out of all the students you walk through, I think maybe a handful of ones that end up going like us and getting math degrees or some sort of stuff.
Right.
I think the bigger idea was that the table you can see putting down, there's some type of pattern going on that you don't make this 2 with n and n minus 1 connection or n plus 1 connection. You don't make that.
Right. A lot of people don't.
Half of them been in there anyway.
And they find out when I pass all the papers.
Yeah, we're in there.
And plus, you guys only had 30 minutes. This was a fairly involved problem for 30 minutes by yourself.
By yourself. You did? You had your college students do?
I would have them do this in like a number theory class, like an elementary number theory class, for sure. Yeah. But then I would expect them to go at least to what we did and probably a lot further than that.
You didn't administer this? This is part of the program or something like this?
Yeah, this is part of the Fostering Algebraic Thinking program developed by
number theory and different things, but if they've already kind of seen it, it's like that type of back to the that textbook.
Oh, so Martha has their hand up.
Hey.
So if you want to share something, Dr. Kip, I'm going to mute my microphone.
Absolutely. So we were looking at this, and one of the comments that Mr. Z made here was that the students' expression of their algebraic reasoning is largely in terms of explaining patterns, and it's a different way of thinking about it than just formulas, because we're looking at students that are probably a little bit younger than high school as far as the sample group here. But I had a personal opinion about this, that the coolest conjecture that I saw in the whole thing was actually from student E. Having written all these things in terms of divisibility and remainders and everything, to have had this idea that prime numbers can only be written as the sum of 2 consecutive numbers, not 3 or 4 or 5. And it'd be really neat to see that student actually go a little bit further to explain that. And then, did y'all have thoughts on that last student, G, we were looking at with the patterns and there were a lot of conjectures there and a lot of seeing patterns, but I thought I was... The what?
Are you asking our group, or are you asking your group so you can tell us?
Oh, I'm sorry, I was asking our group, and I was trying to listen so I could recap and answer. So student G was... Okay, so the student G has a lot of potential to expand algebraic thinking. There seems to be a high level of pattern recognition there. I think, as you pointed out, coming up with the idea that powers of 2 don't appear to be able to be written as sums of consecutive counting numbers. That was a pretty powerful pattern to realize, and one of the least obvious ones. And yet there seems to be an almost complete unwillingness to actually do anything to investigate as to why the patterns are there. The curiosity as to why things work doesn't seem to be evidenced at all.
Anyone here have anything else? Yeah, I mean, a middle school or high school student could do this problem. They might not get to the level of a graduate student or undergraduate student in mathematics, but pretty much anyone can fill out the table, right? And then develop patterns. And a lot of learning algebraic thinking is recognizing patterns. So. And just being able to gather some information and come up with some patterns from it is a pretty important thought process for a student to develop, any student. Whether they go into any math or anything, even science, anything, it's really important to be able to take some data and develop patterns.
I think that would be for middle school.
That's what Dr. Kemp thought.
Yeah, because in other parts of the country, students are really taking algebra at a much younger age. And I think a lot of it has to do with our geographic area only being 100 years old. Odessa was incorporated in, 1903? So when you think about that, yeah, Fort Davis was there, but we had a community in the country Indians out there fighting, 1800s. I mean, we're just, I think that is tied into it as well. And bringing our community up. You always mention the ethnic groups, but I looked into research that it's not really ethnicity, that it's more income based. That if you start looking at the income of the family and how they value education and how, look at the test scores that way versus the ethnic, you see patterns there too. But the lawyer is good at one of the words I'm looking for, people that lobby, the different groups. They want to say, because, anyway, I'm getting off on politics.
So any more thoughts about the student work?
Yeah, it's important that we do this with our kids. Like a lot of the calculus and the number theory and stuff has been so long for me that I don't remember it. And so I really appreciate doing things that are living it out. I'm not going anymore. So we do need
we try to find ways to tie this stuff in with our system we already have, so that we can do.
Well, if you're teaching the kids to think,
Yeah.
because that thing analysis, the synthesis, that's where they're tested at. Can they think? You got to have your work on that. You got to have your vocabulary base, because they don't know that basic vocabulary, but if they're going to.
Well, how many of y'all have already done one of these with your kids? Is your school, did you have to get permission, or did you just did it without asking? I mean, we didn't know if we were, we put it in our lesson plan, but we sure didn't broadcast.
I don't see that for one.
Okay, so now that you've looked at these examples of student work, we don't really know what students these were. They could have been middle school, they could have been high school students. They're in that range for sure between, I think, 6th to 10th grade. So let's pass out your guys' work. Let's move the table. We only have, say, 15 minutes left or so. At least 2 people from each table move, unless you have 2 people. Then. So you need somebody else today? And Lauren, we're going to pass out the work that they did. If you're watching this at home, now you can look at the work that you did on sums of consecutive numbers and think about your algebraic reasoning now that you've looked at 3 other students' work. So I'm going to turn off the microphone. We're going to work on this for 10 minutes, and then Dr. Kep's going to give us a little plug for the conference that we're meeting at for January 9th. So. Dr. Kett, you want to share about the STEM conference, which is going to be our next meeting? I'm going to mute my microphone.
Yes, so we just had a meeting yesterday with Martha Alexander and Diane Utzman and the Region 18 crew. So what we're planning on doing is our January meeting will be covering the registration cost for any of our participants in this project attending this this conference. And I think along with our teacher quality grant project, we'll probably try to have everybody that's connected with our projects meet for one of the sessions, probably in the Mac boring room, just to strongly tie it in with the grant. What they're looking at right now is, first of all, they're excited that we're going to have a lot of people registering. Martha said, as is always the case, they are currently short on speaker proposals. And so I really want to strongly encourage you, as I've been telling the people down here, you know, almost no matter where you are, you're doing something new and interesting or different that's making a difference with your students. Put together a presentation and share it. If you've got a collaborative effort with your fellow teachers, something that would be worth other people replicating that you think works really well, you know, we need proposals. We need talks. You know, God help these poor people coming to the conference. I'm going to be giving 2 presentations, I think, that hopefully enough people will find interesting will be worthwhile. So the link is there. You can go to the Region 18 website, and it's actually the first item on their web page to register for. I would ask you to hold off on registering and let us try to organize that just a little bit. But you can go ahead and do the talk proposals, and we would very much love you to do that. This is the second year that Region 18 has hosted the conference or the UTPB has hosted it, and we hope to make this the annual norm. So we did it last year. It went off pretty well. We got a lot of ideas for what worked and what didn't. And this year's conference, we hope is going to be bigger and better. Notice the date. You will not be too deeply into school, and so the semester won't have gotten too hectic by Saturday, January 9th. That was intentional. We're just trying to find the time that works best for teachers in a semester that's very hard to find that time. So anyway, please, please, please get in there, share what you know, and everybody be safe going home. It's raining down here already, so we're going to close up and head home.
All right, thank you, and we're going to stop here too. So anyone watching this recording as well, the January meeting is at the conference, January 9th, and I'll send more information about which seminar or which talk is going to be required as part of the grants, and the rest you can pick, obviously. Then. So have a good holidays, and we'll see you in January.